We are still in chapter 8. This is section 8-2. This is recording number 2. Okay, now one of the things he does right here is he talks about how do we do our rounding off. I'm gonna just let you guys read that, and all of these situations where we have round off error or round off protocols or round off decisions or round off rules, they're easy enough. You just got to look at them. You got to do a couple of examples. There's no reason for me to take class time to explain those. So let me talk about the example 8-3. Okay, so this is as good of example as any. Keep in mind, as always, these are metaphors. Okay. And can be used, the same concepts, exactly the same techniques and concepts can be used for other types of problems that you may, quite frankly, find more interesting, as opposed to some of these examples don't seem to be that interesting. But they're metaphors, and you can use the same techniques for other types of problems that you find interesting. So we're talking about ages of medical doctors. So the researcher believes that the mean age of medical doctors in a large system is older than the average age of doctors in the United States, which is 46. So as you read this problem, bear with me on this, and please take my advice. I mean, I think I'm giving you good advice. Write down the information. Write down what you're given. So you should write down given, okay, given, number 1. Now, of course, you can organize it any way you want. You don't have to write down the numbers. That's what I typically do. Point number 1, point number 2, point number 3, and so forth. But do whatever makes sense to you. But write down what you're given. So the given information is that we take a random sample of 30 doctors. Therefore, n is equal to 30. Okay, next item. I like to write down what is the random variable. If you cannot clearly state what the random variable is, you're going to have some problems, right? So the random variable is age of the doctors, okay? Okay, the next thing I would write down is I would write down the mu, that's the, I'm sorry, I'd write down the population. I'd say the population is all doctors in the United States. Okay, then I'd write down mu equals 46, and then I'd put a little note. Mu is the average age of all doctors in the United States. Okay, I would write down the sigma, that's the standard deviation of all doctors in the United States, is 4.2 years. Now, do you see what I'm doing here? I'm being so simplistic. You're going to think that I'm treating you like a 5th grader, but I'm not. If you cannot articulate this and write this down clearly, you're never going to be able to solve these problems. So take that extra step. Write down what the random variable is. Write down what the population is. Write down all this stuff so that if somebody asks you, you will be able to say it. Or if your 8th grade nephew asks you that question, you'll be able to explain it to him. You should always be able to explain this stuff to an intelligent 13-year-old. Okay, so you write down all that information that you're given, okay? So then the next thing I'd write down is X bar, that's X bar equals the mean age of the sample. So I'd say X bar is the mean age of the sample. X bar equals 48.6. Okay, so do you see what's going on here? I've got this sample of 30 doctors. I ask them their age. It's 48.6, and I compare that to the average age of doctors in the entire population, which is 46. Did I say that right? The first one here is 48.6. That's the X bar that I measured, and this is the mu for the entire population. Okay, so now, if you were a talk show radio host, you would look at this information and you would say, well, obviously with air quotes, obviously the age at this large system is older. Look, we measured 30 people and their average age is 48.6. On average, it's 46. Now, you see this all the time on the news, right? You see it all the time in government. You see people making these kinds of ridiculous statements all the time. But it's not scientifically valid because you have not done the statistical test. Okay, so now it says test the claim at alpha equals 0.05. So that's my error budget. Now the only other thing I need to look at is the claim is going to be, what he believes is that the average age is older than the average age in the population. So that's a one-tailed test. So that's all I need to know. I've got everything written down that I need to know. So now here's the solution. State the hypotheses. Well, the hypothesis is, the null hypothesis is that the mu is 46. In other words, it hasn't changed. You know, the null hypothesis is the status quo, basically, okay? And what the status quo is saying, what the null hypothesis is saying, is that, hey, you took these guys out of this hospital, this large hospital, and that, just because they're a little bit older, that doesn't prove that they came from a different population. They came from the same population. The alternative hypothesis is saying, no, you're wrong. Your data is old, or you misunderstood things, or whatever. The fact that I got a average age of 48.6, that proves that I came from a different population. My population has a mu that's greater than 46. Therefore, we should reject the null hypothesis. Okay, so now we got to find the critical value. We did that previously. The alpha is 0.05. That's my error budget. It's a right-tailed test, so all I have to do is find the z value that gives me 5% to the right of that particular z value. The critical value then is 1.65. Okay, now have I mentioned lately how important it is to draw cartoons? Draw the cartoons. I am telling you, draw the cartoons. So here it is. Here's the cartoon. Okay, 1.65. That's my critical value. I've got this cartoon here. To the right of 1.65, that's the reject region. That's 5% of the time you're going to be over there just by random chance. Okay, you got that? Just by random chance, you pick however many doctors. You pick 30 doctors, and you measure their X-bar. The X-bar of those of any 30 doctors that you pick by random chance is going to be over here. So if I land over here, I reject the null hypothesis, but I am going to be wrong 5% of the time. That's the essence of hypothesis testing. So if 5% is over here, 95% of the time, everything's going to be over here, and that's why we do not reject. Okay, excuse me, I may be off the screen here a little bit. Let me fix this. Okay, I may have been off the screen there a little bit. I apologize for that. Okay, so I hope by now you've done enough of these in the first section where you kind of get the idea of how to compute the critical value, how to compute the, how to make the decision. Okay, so we find the critical value. We know what that means. Now we're going to compute the test value. Here's the formula. I'm going to strangle you if you don't write down this formula every single time. Write down the formula every single time. Once you write down the formula, then it's very, very easy to plug in the actual numbers. Once you plug in the actual numbers, it's all done on your calculator anyway, and here's what you come up with, 3.39. So the test value, 3.39, the critical value, 1.65. Now you make the comparison, and 3.39, by golly, it's over here. It's in the reject region. So you reject the null hypothesis. So that's step 4, making the decision. 3.39 is greater than the critical value of 1.65. Therefore, we make the decision. We reject the null hypothesis. Okay? And then you summarize the results. This is an important step that you will be tempted to not do, but you should do it. If you cannot summarize, you don't understand. And when you go out there and you're working for somebody, and getting paid money to do this job, they want an explanation. They want an explanation that people will understand. So you got to be able to summarize it. So you should be able to summarize this by saying, hey, there is enough evidence to support the claim that the average age of the doctors in our system is greater than the national average of 46. Okay? So do you see how this could be easily modified to be a different kind of a problem? This could be so easily changed, but the concepts are exactly the same. Maybe you're talking about whether or not you know, your kids are smarter than the national average. Maybe you're talking about whether they're taller than the national average. Maybe you're talking about, you know, do, do people in the nursing home, do they get sick more often and die from COVID disease more than the national average? So all of these are typical scenarios that you can cover, you can solve with this technique. Okay. Now here's a comment, very important. In example 8.3, that's one we just did, the difference is said to be statistically significant. So this is the difference between a scientist and a talk show radio host. A talk show radio host would say, well, obviously there's a difference. It's 48.6 compared to 46. That's a big difference, right? And it is a big difference. It's close to 10%, right? 10% of 46 is like 4.5. So, you know, it's a little less than 10% difference. So a talk show radio host would say, yeah, there's a big difference. Well, it's not a big difference. And the reason it's not a big difference is because the yardstick down here, you have to look at this difference up here in terms of the yardstick, and in terms of the yardstick, it's not that big. Now I just don't have the software to do the calculation for you, but if you calculate this out, you'll see what I'm talking about. You've got to, I could probably do it offline. Give me 1 second. Okay, so I grabbed my calculator. I calculated this right here. What I come up with is 0.766. Okay, so that's your yardstick. How many units of 0.766? How many units of this standard error are you surprised? Well, I'm surprised 3.39. So yeah, I am surprised enough. I am surprised enough. I've gone out far enough in terms of, or using the yardstick of the standard error, I've gone out far enough that I reject the null hypothesis. But unless you do that mathematics, you cannot, as a scientist or as a rational person, you cannot make this decision. Okay, so I'm going to get off that soapbox. I hope I've convinced you how important this class is. Okay, and then before I went off on this rant here, he made a comment here. What we say is that the difference is statistically significant. Now, obviously there's a difference, but is it statistically significant or not? So if it's, when we say statistically significant, what we are talking about here is that you have enough of a difference that it will only occur by random chance a certain alpha amount of the time. So alpha is 5% in this case. By random chance, you'll get the same result only 5% of the time. So you could be wrong. Absolutely, you could be wrong. There's no guarantees in this business.